Let's talk about functions and their inverses. A relation is just any set of ordered pairs, but in order for a relation to be a function, y is a function of x if for each x value there is only one y value. The graph of the function passes the vertical line test, and it's written as y equals f of x. Your domain is the set of all x values, assuming y is a function of x, and the range is the set of all y values, assuming y is a function of x. So determine whether each is a function of x, whether it's a function, whether it will pass the vertical line test. This right here is just a line. All lines are functions, so yes. This, what is that? X squared plus y squared equals 1? That looks familiar, doesn't it? Oh, it's the unit circle. So it is a circle around the origin whose radius is 1. That definitely does not pass the vertical line test. So no. This one is an upside down parabola moved up 1. That's definitely a function. It passes the vertical line test. This is the same as x equals negative y squared plus 1. Very similar to what we had over here, except when the y is being squared, then I have a sideways parabola, and a sideways parabola does not pass the vertical line test. So this one is not a function. Given f of x is equal to 3x minus 1 and g of x is x squared, find the following. For f of 10, we're just going to plug in 10 in x in the f function. For g of x plus delta x, we're just going to plug in x plus delta x in the g function. So instead of x being squared, it's going to be x plus delta x being squared. That is equal to, if we expanded that, x squared plus 2x delta x plus delta x being squared. G of f of x is a composition of functions. It means in the g function, we're going to replace the entire f function for x. So x is being squared in the g function, and instead of x, I'm going to replace it with the entire f function. So 3x minus 1. If we expanded this symbol right here is also a composition of functions. It's asking me to put g inside of f, the opposite order of what we did in number 7. Instead of the x in the f function, I'm going to replace it with the g function, which is x squared. 3 times x squared minus 1. That's it. To determine the domain and range for each function, remember there are restrictions, such as for square roots, you cannot square root a negative number, and for rational functions, you cannot divide by 0. So let's determine our domain and range. Square root of x just looks like this, and so if it's square root x minus 1, that means we've gone to the right one. That means our domain starts at 1 and goes to positive infinity. And our range starts at the y value when we plug in 1, and that would be 0 all the way to infinity. Here we have a rational function that has a vertical asymptote, and that vertical asymptote is at x equals 2. So our domain will be everything except that. And our range, well, do we have a horizontal asymptote? We do at y equals 0 because the degree of the numerator is less than the degree of the denominator. So I believe 0 will also not be used. Negative infinity up to 0, and from 0 to infinity. Our domain for number 11 is looking at this graph. We have 2 vertical asymptotes, one at the y-axis and one at 2. So our domain will be negative infinity to 0, 0 to 2, and 2 to infinity. In our range, it looks like we have a horizontal asymptote at 0, so we go from negative infinity to 0 non-inclusive. Up here, we have the lowest value that this upper part of the graph touches is the y value of 1, and it is inclusive. It actually has a point there. So we'll go bracket 1, comma, all the way up to infinity. A one-to-one function is a function in which not only there's only one y for each x, but there's also one x for each y. So a one-to-one function not only passes the vertical line test, but also passes the horizontal line test. An inverse function is found by switching x and y, solving for the new y. F inverse of x is the symbol for the inverse of f of x. Only one-to-one functions have inverse functions. Since x and y are switched to produce the inverse, the domain of f is the range of f inverse, and vice versa. If a comma b is in the function of f is a point, then b comma a is a point in the function of the inverse of f. All right, so which of the relations in examples 1 to 4 is a function with an inverse function? First of all, our only options would be 1 and 3. 1 is a line. A line definitely passes the vertical and horizontal line test. So our equation in number 1 is 1 to 1. But what about number 3? This is a parabola, and a parabola passes the vertical line test, but it does not pass the horizontal line test. So number 3 is not 1 to 1 and does not have an inverse, or its inverse has restrictions. Find the inverse of f of x equals 2x cubed minus 1. The steps for finding an inverse function is to first replace f of x with y. Because the domain and range are switched for inverse functions, we're going to switch x and y, and then solve for y. We have our inverse function. Let's go ahead and call it by its name, f inverse of x. There's our inverse function. A piecewise function is a function defined differently on different pieces of its domain. For example, when x is less than or equal to 0, our function is just x. And you can see that for the piece less than or equal to 0. When x is between 0 and 1, we have the line 2 minus x. This right here is classified as a jump or a break in the graph. And from x greater than or equal to 1, we have x squared. So when the x's are greater than or equal to 1, we have the part of a parabola. Graph this piecewise function and give the domain and range. Absolute value x for all the x's less than 1. Remember, absolute value x looks like this, except we only want it to be less than 1, so we'll make it a partial view like this. And this is only x is less than 1, so our hole will be here. Unless this piece connects, then we won't have a hole. But let's take a look at this piece, x plus 2 when x is greater than or equal to 1. So that is a line with the y-intercept of 2 and a slope of 1. And it's only defined for 1 to infinity. Our domain is, even though we have this break or jump, 1 is still in our domain because it's defined up here. And everything to the left of 1 is in the domain because it's defined here. So our domain is actually negative infinity to positive infinity. Now our range is concerned with the y values, and we do have a minimum y value. Looks like we don't go below the x-axis, so our lowest y value being used is 0, and it is included. It is a value, it's defined there. And then all the way up to infinity is being used for the range. You may want to try to include this jump, but notice that the numbers between 1 and 3 on the y-axis, though they're not being used over here, they are being used with this part of the absolute value function. So everything above 0 and including it is in our range. Now zeros are x values for which y equals 0. Conventionally, zeros are written as just like single values, but intercepts are written as xy coordinate points. Find the zeros without using a calculator. So we're going to make y, or f of x, equal to 0. Look, I have a quadratic function, and I think I can factor that. -4, +1. All right, so x is equal to 4 and -1. Those are my zeros. If I were to write them as x-intercepts, it would be 4, 0, and -1, 0. To make a rational function equal to 0, we essentially make the numerator equal to 0. As long as it doesn't also make that denominator equal to 0, then those values are the zeros of the rational function. This is actually the difference of perfect squares, so it can be factored to be x plus 2, x minus 2. So our zeros are -2 and +2. And that's our review of functions and inverses.